From the University of Chicago, this is Big Brains with Paul M. Rand. Conversations with pioneering thinkers that will change the way you see the world.
As you'll hear, I had a lot of fun recording this episode with neuroscientist Bobby Kasthuri. Bobby's working on some pretty astounding stuff in an effort to map the human brain. There are trillions of neural connections in the brain, and Bobby believes that altogether, they make up everything that makes us human. To map all those brain cells is a harder task than counting all the stars in our galaxy, not that Bobby isn't going to try. Don't forget to rate and review Big Brains on Apple Podcasts or wherever you listen to the show. All right, well, Bobby, I have to tell you, I've been a little nervous about having you come in. The name of this podcast is Big Brains.
Okay.
And I was kind of terrified you were going to say, well, that's a really stupid name because big brains don't equal more intelligence. Because here I am talking to a foremost neuroscientist and brain expert. So I guess tell me, maybe right up front, does big brains equal more intelligence?
Actually, it's an interesting point because I'm interested in this idea of size and intelligence. And in general, when you think about animals that are smart, humans, whales, dolphins, elephants, they all have big brains. But a better measure is the ratio of the size of your brain to the size of your body. And when you use measures like that, then things like whales and elephants, which normally just by absolute size would be smarter than us, kind of scale more closely to us.
But big brains can indicate if it's proportionally more intelligence.
Exactly.
So the podcast actually is appropriately named. All right, so I'm going to back up now that I feel relieved that my name of the podcast is not completely
Big
wrong.
Relative Brains.
Big Relative Brain. Little long. So let's talk about how you got to the university. How would you describe what you do now?
One way to describe it is we are anatomy on steroids. There has always been a place for figuring out the structure of the brain. What does the brain look like at various scales, at the whole brain scale, at the single cell or neuron scale? But it was always done in a kind of like cottage industry fashion. You have a little lab, I do my little part of it, someone else does another little part of it. I want to do that at industrial scale. I want to turn anatomy of the structure of the brain into what we did for the genome, which is we collect these enormous data sets that most people can't access and then distribute them widely to the community. We generally talk about three things when we think about if we had a full map of a brain.
Can I clarify this? When you say a map of the brain,
yes,
what does that literally mean?
Yeah, so for about 100 years now, neuroscientists know that your brain isn't made up of a little person inside of you. For a long time, there was this theory, it was called the homunculus, and it was this idea that there was a little person sitting inside your head who also had eyes and arms and legs and et cetera. And as they moved their arms and legs, your arms and legs moved. It was an instantiation of you. But over time, we realized that the only thing that's in there are cells. There's nothing magical or human like you inside of it. And in fact, we think that in a human brain, there's 100 billion brain cells or neurons. And the special thing about neurons that's different than any other cell in your body, a stomach cell, a skin cell, is that neurons make long connections, processes that connect with each other. On average, in a human, each neuron makes 10,000 connections. So if you take the number 10,000 and you multiply it by the number 100 billion, you get an even bigger number. That's something like a quadrillion or whatever. Yep. I don't actually know what that number means, but one way to think about it is there are more connections between neurons than there are stars in the Milky Way galaxy. And I want to map every one of those.
And the purpose of mapping that means you'll be able to trace, start, finish, links, everything else.
Correct.
And to what benefit?
At a very high level, the strong hypothesis in neuroscience is that that map of connections is everything about you. Like if we could decipher that map, and we should talk about how one would decipher that map, but for now, let's just say we could decipher that map would have every memory you've ever had. It would have every one of your hopes, your dreams, your skills, your fears. Everything about you is stored in that map. Now, that's a very high level, but what could we do if we had a map like that? I would say the first thing we could do is, and you and the audience might hear, every day we hear about how machine learning or artificial intelligence algorithms do something better than a human being does. Now, an artificial algorithm can beat a human in chess. An artificial algorithm can beat a human in Go. I recently learned that an artificial algorithm can now beat humans in poker. That last one bothers me because that involves deceit and bluffing and et cetera. And those algorithms are better than us at that, right? But the thing none of them can do, which our brains do all the time, is that in addition to playing a game, our brain knows how to move my body, sit down at that table, recognize the chessboard, and move my arms with skill and grace that no algorithm can currently do. So if we had a map of the brain, I'm hoping we can reverse engineer many of these human qualities, creativity, empathy, sense of humor, that ultimately there's going to be a physical basis for that. And if we know that physical basis, we can reverse engineer it. So soon our algorithms and our robots will do the same thing.
Let's talk about both sides of the coin of being able to do what you're talking about doing. There's a terrifying side,
absolutely,
arguably, to what you're talking about doing.
Absolutely.
And then there's hopefully a positive side.
Yes.
Let's start with the positive side.
Yes. So maybe we'll agree if a robot has a sense of humor. I think that's a positive side in and of itself. But the other thing that I tell people is that your brain, everyone's brain, Einstein's brain, Mozart's brain, they all operate at 20 watts of energy. And these light bulbs in this room are probably 60 watts of energy. So although you may consider a lot of humans dim bulbs, they are in the sense that they can perform tasks at energy levels that we can't comprehend for any of our algorithms. And because half the time I'm at Argonne, which is a Department of Energy lab, I've learned that by 2025, by 2030, the single largest growing fraction of our energy budget is not the oil that we put in our cars or in our airplanes. It's uploading and downloading pictures to the internet.
Okay.
And by that time, just moving information and the amount of information that we move is going to be the single largest part of our energy budget.
My gosh.
And so if we understand how a brain can move information and do calculations for 20 watts of energy, that could significantly help us in our energy crises.
That is a very unexpected answer, but a very interesting one.
Another one is that for many psychiatric and mental illnesses, we don't even know where the illness occurs. We don't know, although we think that many illnesses like autism or schizophrenia are misconnections, neurons that are connecting with inappropriate neurons. We have no idea where to start. And if we had a map of that brain, and compared it to a map of a schizophrenic brain, we'd start to understand what the physical basis of these mental illnesses are. And the belief is that once we understand the physical basis of these mental illnesses, we'll be able to treat them in a more rational fashion.
So those are some wonderful upsides on the side there.
Yes.
But even as you were talking and making the joke about the game theory and the poker playing, you start linking into things that could be a downside. And if there's fears about artificial intelligence, those fears could go into overdrive for some of the stuff that you're talking about.
Absolutely.
What do you do about that?
Nothing.
Okay. That's for somebody else to worry about.
Yes. A great physicist that I sometimes think about, his name was Robert Oppenheimer. And he's often called the father of the atomic bomb. And when they interviewed him and they asked him, and they say, you care fundamentally about how the nucleus works, or et cetera, but you realize that that kind of science can have applications for making bombs, destroying cities, et cetera. And he says, I can't help myself. I need to be able to know how the nucleus works. And if society takes my applications and applies it however it wants, there's nothing I could do about that. And I feel
it's going to happen at some point.
Correct. And the one thing I can't seem to give up is my curiosity about how the brain works.
Right. If you're listening to Big Brains, there's a good chance you consider yourself a lifelong learner. However, you may not know about the University of Chicago's Graham School and its focus on continuing liberal and professional studies. For more than a century, Graham has been a destination for lifelong learners. They offer courses online and in the classroom, bringing the transformative education UChicago is known for to students of all ages. To learn more about the courses, certificates, and degrees, visit graham.uchicago.edu. You are pretty keen, ultimately, on trying to map a mouse brain.
Yes, the goal itself is data. The constraint is data. So a fly brain, which is somewhere in between the original worm brain that was done, I think, in the middle 80s or the early 90s, and the mouse brain that we want to do, and ultimately the human one, because there are, as I said, a quadrillion connections in your brain, The only way to make sure you capture every one of those connections is to image the brain at very fine resolution, at very high spatial resolution. Meaning, when we take pictures of the brain...
And you slice it very thinly, is
correct.
that right?
It turns out that there are so many connections in your brain. Each of them is unbelievably small. In fact, they are so small, they're smaller than the wavelength of the light that you use in most microscopes. The connection is actually smaller than light. So we can't use light microscopes to map the brain. The only kind of microscopy you can use is something called electron microscopes. So the only way to do electron microscopy is to make really thin slices, physical thin slices of a brain, any piece, any organ, and use an electron microscope to take a picture of each of those slices, physical slices, and put it all back together inside a computer. We probably do thousands and thousands of slices, and we take a picture of each slice.
Okay.
The reason we have to do that is that there's so much material packed into there. Our microscope has to be able to resolve things that are the difference between atoms, hundreds of atoms. At the nanoscale, what we call nanometer range, is the resolution we need to apply over the entire brain. Now, if you need nanometer resolution over a brain that's 1 centimeter, you soon start to collect enormous amounts of data. And so a lot of the reason that this couldn't happen before is that the mouse brain, the thing that I want to do, and I have to remember this every time, is not 1 million gigabytes of data, not 1 billion gigabytes of data. It's 1 trillion gigabytes of data to do an entire mouse brain where I get every connection between every neuron. To give you an idea of how big that is, if you took all the written material in the Library of Congress, and to a first approximation, let's just say that's all of human knowledge, right? That is not even 1% of the data that we'd like to collect.
Got it.
If you added all the audio that had ever been recorded and put into the Library of Congress, every movie from black and white to 3D today, you still wouldn't get to probably 20% of the data for an entire mouse brain.
My goodness.
So the main constraint is it will be a data set collected about a single thing bigger than any data has ever been collected in the history of humanity.
And the point of then being able to have the ability to collect the data, store the data, manipulate the data,
Correct.
really starts becoming the biggest task of all.
It has, I think, for the last 5 to 10 years actually been the largest problem. But like most obvious problems, it takes a long time for people to recognize it.
But now it's beginning.
And it is clear, not just the work we do, but in almost all fields of neuroscience, people are collecting more data than they know what to do with.
I mean, are there 100 people around the world trying to do what you're doing? Is it collaborative? Is it competitive?
It's everything.
It's all those things.
It's humans working with humans.
Right.
Which entails all of the things that happen when humans work with humans. But I would say the number is not 100. It's closer to 5, probably 4 or 5 groups. I would say in the United States, there are about 3 or 4 groups that are targeting. There's one place called Genalia that's targeting the fly brain. There's Allen, which is targeting a smaller part of the mouse brain. There's us and probably Harvard. Worldwide, there's a couple of Max Planck institutes. These are the sort of the large premier scientific institutes in Germany that are also participating.
If we think through what the ultimate goal of this entire project might be, what do you think it is and how long do you project it would take to get there?
Let me pick one, and the one that I'm the most interested in, which is what does it mean to be a human? What is so special about a human brain that's different than a primate brain, than a mouse brain, than a fly brain? And to some first approximation, they're all the same. The genes that a mouse neuron expresses are very similar to the genes that a human neuron expresses. Okay. The channels that let in the ions to do the electrical activity in a mouse neuron are pretty similar to the channels that let in the ions to do the electrical activity of a human brain, right? So we think since there's no difference in kind, the neurons are all the same. Neuron is a neuron is a neuron. It must be the map of neurons, the actual connection map, that's the difference between those two. Okay. Now, I'm not sure that requires an entire mouse brain to be compared to an entire human brain to get that answer. So I actually know, I think, what the difference is between a human brain and a primate brain and a mouse brain.
Okay.
The main difference is that, and I have 2 kids, and I hope they're not listening. The main difference is that humans are born completely useless. When you bring home your baby for the first time, you realize that without you, that baby dies. That baby literally knows nothing, right? And that is uniquely different than any other animal born. Most animals born have a set of behavioral repertoires. A fly born knows how to fly, which is actually a pretty amazing thing to solve in 3D space if you can. And what's fascinating about humans is that we're born completely useless. But the same human, my children, learn a set of skills that can't be in their genomes. There is no gene for learning using the iPad. In fact, there's probably not even genes for reading because the printing press was only invented a couple of hundred years ago. So what I think is interesting about humans is that we're born useless, but have a capacity to learn new things that no other brain has. The other way I give this argument is, and it's clear, I'm so much smarter than my daughter. I know how to drive a car. I know how to do alleged taxes, grocery shop. There's a set of skills that I have that she clearly doesn't have. So in almost any test, you would, if you didn't know who we were, you'd say this unknown person is way smarter than this unknown person, right? But there is one way where she dominates me. And this is this thought experiment, which is that if you took us and you put us down in any location in the world, and you came back 20 years later and said, who's assimilated better? I guarantee my daughter, other than skin color differences or hair color differences, will be indistinguishable from the population that you put her down. Okay. I'll either be dead or still stick out like a sore thumb, right? So
she's learned.
Yes, human brains are born in this kind of tabula rasa, blank state condition and have a capacity to learn that other animals don't. And that's the kind of physical basis that I'm interested in trying to figure out.
Energy powers our modern world, fueling innovation and improving living standards across the globe. But it's one of society's greatest and most complex challenges to deliver access to reliable and affordable energy without putting our health, environment, and climate at risk. For a deep dive into today's policies and trends driving solutions to the global energy challenge, listen to Off the Charts, a podcast of the Energy Policy Institute at the University of Chicago. We'll provide analysis from UChicago experts, as well as government and industry leaders, all grounded in the latest data-driven research. Listen on our website at epic.uchicago.edu or wherever you get your podcasts.
Let's talk about how you got to the university, what you do.
Yes. When I was in college, I was really interested in being a doctor. That was partly me being interested and then my parents making sure I was interested in being a doctor. And when I got to medical school, the field that fascinated me the most was psychiatry. Psychiatry and neurology, things that have to do with the brain. Like most students, I was interested in helping people, saving the world, etc. And when I got there, I realized, despite the fact that many psychiatrists, neurologists, they're brilliant, off the charts brilliant, the fields themselves are like wild, wild west. The therapies that we use on people for psychiatric illnesses, they're never thought out a top-down kind of therapy. In fact, they're often drugs that we use for other diseases that we try for these diseases, we get some success, and then we make that the standard of care. I was really disappointed with how we treated psychiatric illness and mental illness. And I realized the patients had a little contribution to this too. I realized that the thing that I could do the best was not continue the same vein of sort of ad hoc therapy, but try to figure out something about the brain that would ultimately help us understand mental illness.
That was a pretty big switch for you.
I didn't enjoy medical school as much as I thought I would.
Okay.
I thought it'd be like House. You show up and you're just solving intellectual problem after intellectual problem. Turns out that's not what the majority of medicine is anymore. And so it was a switch, but I think it was always here.
So let's talk about then why you're at Argonne and the choice to be there.
Yes.
Along with being at the University of Chicago.
Correct. So Argonne is one of these national labs that is funded by the Department of Energy. They have currently, I can't remember the rankings, but the fourth largest, strongest, handsomest computer in the world. And they're one of the few places. There's very few academic centers, academic universities in the world, where as a young scientist, you could show up and say, listen, I'd like to collect 1 trillion gigabytes of data. I don't really have any money for the computers. Maybe you guys could help out. I couldn't find a bunch of places that said yes to that. But when I showed up at Argonne, they said, yeah,
we can do this.
That seems cool.
That's pretty. Now, you had thought if you could obtain $15 million, is
Yes.
that number, that you could get this done in a year and a half. Is that still?
I mean, since we're on the record, let's make it 25. Just in case.
Sure.
But yeah, on that order of magnitude. Now, to be fair, that number is to collect the data.
Got it.
I don't know if anyone other than one of our close collaborators at Google knows how to analyze the data.
And Google's involved in this with you, aren't they?
It is amazing. So we can collect all of this data, but what we really need are, and we calculated this, if you calculate all the humans that currently live on the planet, and you make an estimate for all the humans that have ever lived on the planet, and you say, I'm going to have every one of those people work a 40-hour week and trace all the neurons in a mouse brain. It's still going to take something like 10,000 years
Wow.
to analyze all of that data. I might be wrong. It might be 1,000 years, but we'll all be dead anyway, so it won't matter. And so it turns out that the only way we can imagine this working is if we get algorithms that can see the same things in the data sets that humans see. And Google is not for our work, but in a lot of other work, self-driving cars, recognizing people in pictures, they're deeply invested in this space called machine learning
Right.
or artificial intelligence. Right. I didn't do this, but some very smart neuroscientist who's a collaborator of ours convinced Google that if they could crack this problem, they could crack any problem.
So they're
in this space. And so I really think they currently, amazingly, have the best algorithms in the world for analyzing mouse brains the way we collect the data.
You wouldn't think that about Google off the top of the chart, would you?
No, but although I will tell you, they are moving more into the medical space almost every year.
Simply because of being able to have the data and
Yes.
the need for data to do this.
Yes.
Okay, fascinating. So if we look out and think through, well, what's the path that you're on right now?
Yes.
And where do you see and what's happening over the next 5 years?
The hard part with human brains is people have to give us samples.
Yes.
And for most
Thanks
medical
for not asking for one when you came in, by the way.
for most medical conditions, it's hard to get a brain biopsy. So in the mouse, we want to learn general principles of how the disease works. But even this field is moving so fast. There's a set of scientists here and a set of scientists worldwide that are now being able to take a skin cell from a human being, turn it into a stem cell, a cell that can make anything, and then turn that stem cell into a 3D mini brain from them. And apparently that mini brain contains if the person had epilepsy, a genetic,
It would be in there.
it would be in there. If the person had schizophrenia, it's in there. So now that is a volume we can analyze before or after we deliver drugs, et cetera, and then make predictions about the actual human to really personalize therapy. Now, this is just a frontier that's starting, but given how fast science moves, maybe in 5 years, you will be able to have your own personalized brain in a dish where people can analyze that brain and then make predictions about yours. For me, it's hard to say how it will go 5 years from now, but all these threads are happening at the same time. So it's hard for me to believe that in 5 to 10 years, we don't really fundamentally understand brains, not just as things that contain the soul, but as things that are like computational units. We will start to even understand the brain as a device, as a computational device, way more than we understand it now.
It's a good time to be alive, isn't it?
Yeah, or scary too. I can see the scary part.
All right. Well, it is a delight having you here. I can't wait to keep reading what you're doing and accomplishing. Thank you for coming in and sharing your time with us today.
Thank you very much for having me.
Big Brains is a production of the UChicago Podcast Network. To learn more, visit us at news.uchicago.edu and subscribe on iTunes, Stitcher, Google Play, and wherever else you get your podcasts. Thanks for listening.